Okay, it's my great pleasure to introduce Sammy for tonight's event, and he got master from NYU just this summer and just finished our 12 weeks weekend, and he did really good job. And today is the opportunity for him to present the most popular algorithm in Kaggle competition so far. And actually, it's made by his college mate back in Shanghai, so it's a coincidence.
Yeah, just coincidence. We also is it's actually from the same university on the degree.
Great. Let me try to zoom the. Okay, great.
Okay, so hi guys. Since we just got 3 audience here, so I think it's we have enough time for I don't know you to introduce a little bit yourself to other guys. So let's start from myself. Okay, my name is Lee John. It's my Chinese name. You can call me Sammy if you want. So as you said, I took her 12-week science bootcamp, and this I used the XgBoost in my Kaggle competition, the project I did, and the final result is I reached a top 10% on the final leaderboard, and this is my first time to do a Kaggle competition, and hopefully I can do much better in the later competition, but it's top 10% is actually, I think it's okay for my first try.
Hi everybody, my name is David. I work at AIG in Risk Analytics. I've taken Vivian's Intro to R and Intermediate Data Science in R, and it's been a good experience, and I'm just learning what I can.
Hi guys, I'm Antoine. I just moved from Montreal to New York months ago. I'm a data analyst and looking forward for the presentation.
Where do you work?
I'm looking for a job actually. I just lost my job in Montreal to try the challenges of New York City.
Where?
Montreal? Yeah, Montreal.
Can you introduce yourself?
Yeah. So my name is Ravi Rao. I've done a lot of things in my life. So I used to work at IBM before, research, and I did some consulting, and I'm also dabbling in data science, trying to look at public data sets, especially in the healthcare area. So I'm going to present a paper in that the conference next month. And so I'm bored that for the last 3 months.
Are you still with IBM?
No, I'm not. I'm now teaching at Iterative University in the engineering department. So I'm trying to keep my other interests alive and going. Maybe this will become a research area of mine.
Very good.
Okay.
Seems to be coming
You
up.
got it.
Okay, so now let's move on. So there are 3 parts of today's presentation. First one, a very short brief introduction to XgBoost, because I just talked with David before we start this presentation, and we think most of people are interested in how to use XgBoost in the Kaggle competition rather than to really understand this complicated algorithm we really do. So there are only 2 slides that contains mathematical or technical stuff. So I promise you all the content, most of the content sides are very high level. Most of them are intuitive. So for the second one, I will do some quick implementation of shows my job, what I did in my Kaggle competition, and just give you some hands-on experience of how to use the XgBoost to compute in Kaggle, and finally the Q&A. But you feel free to interrupt me if I say something wrong, or there are some points you need to you want me to explain again. So let's get started. So should be So what is XgBoost? You can find these words on the GitHub page of XgBoost. It says it's XgBoost helps blah 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 with the Kaggle competition blah blah blah. So it's just like showing off the old traditional classic algorithms. These old guys they are not computable in this today's Kaggle competition. So when people saw this one, I said, okay, what happens to random forest or gradient boost machine or other algorithms. Why this new guy come here and just build them all? So people are interested in that. So that's why we want to dig into this XgBoost. So first we need to find out the full name of XgBoost. It's called Extreme Gradient Boosting. So you can tell from its name that actually it comes from gradient boosting. So how many of you have heard of gradient boosting? Oh, great. So yeah, how many of you have heard of random forest if you haven't heard of gradient boosting? Okay, great. So you can tell from its name, it's a variant of gradient boosting, which is a tree model based supervised learning algorithm. So, even if you haven't heard of the gradient boosting, it's okay. I have a couple of real life examples showing you how to do this gradient boosting stuff. So it's okay. Let's just move ahead. Okay. So So this is the third point, the introduction of the gradient boosting machine. So it says, unlike fitting a single large decision tree to the data, which amounts to fitting the data hard and potentially overfitting, the boosting approach instead learns slowly. So after you read this sentence, maybe you want to ask this one. So why is it called boosting when it tries to learn slowly, right? Actually, someone asked me this question before, and I cannot answer this question. But I did some Google search and found that actually boosting is actually an ensemble method. So the boosting part is not means it how to say that the boosting part is the algorithm used to minimize the objective function is called stochastic gradient descent, which is super fast. So I guess the author of gradient boosting machine is trying to invent some fancy name, trying to invent some fancy name to convince people, okay, this one is super fast. So this is just a short story of how it comes. Okay. So as I mentioned, let's go back to the previous one. So it is a variant of gradient boosting, which is a tree model-based supervised learning algorithm. So there are two points here. The first one is it is a supervised algorithm, which means for real life problem we have supervised learning. For machine learning we have supervised learning and unsupervised, and also this is the tree model-based, not the linear regression. So 2 points. One is supervised learning. The second one is tree regression, tree model. So let's first do some recap of supervised learning. So for a supervised learning one, usually we were given a training data set with the yi as the output and the xi as the input. So here usually this xi, the input is a vector. It's not just a single value, it's a vector of dimensions. Suppose here is dimension of d. And our job is to build a model trying to make prediction of y hat given the xi as the input. So how do we do that? Usually we use the parameters. So here we define a parameter called theta as a set which contains this wj. J comes from 1 to d. D is the dimension of the x. So here the w stands for weight. I choose w to make it intuitively. So here the weight means, let's take this linear model as an example. So this y hat equals to the sum of this wj times xij. So you can see j from 1 to d. So let's say this example here. So suppose y equal to 0.2 times x0 plus 0.3 times x1 plus 0.5 times x2. Actually, you can intuitively think that you are putting 20% of the weight of y to x0, and 30% of the weight of y to x1, and 50% of the weight of y to x2. So that's why, so this is my intuitive understanding of putting these parameters. So we got this theta here. So our y hat is the sum of the parameters times the input. So our next job is how to find the best parameters, right? So to get this y hat. So remember our job is to make a prediction of y hat. So how to calculate y hat? We need the parameters. So our next job is to find, okay, what is the parameter? So right now, when people are doing this job, people usually define what's so-called objective function. A general form of objective functions like this. We remember the theta is the set of all the weights. So the objective of theta is equal to L theta plus omega theta. So what is L theta and omega theta here? The L theta is what we usually call training loss, which measures how well the model fits on the training data. And the omega theta stands for the complexity of the model. So, well, this one doesn't give any too much details about how to do the calculation. So let's see some example of the training loss, which is the L. So you can see here we define L as the function of y and y hat. We have several famous or traditional define of this loss. So suppose you can see it's a square loss, which is used for visible linear regression. It's defined as the difference, the sum of the errors. So if yi hat equals to yi, so this loss function is equal to 0, so which is perfect. So we have, for the logistic regression loss, we have a similar different definition of this loss function, and so for different tasks we have different equations. So then, what about this regularization part? This omega of w. So remember, w is the weight, the different weight of the predictor or the x. So here two traditional definition of it is L1 norm and L2 norm. The equation is quite simple. It's just the lambda, which is a parameter. Just usually it's very small. Just put it, and for the L2 norm, it's just lambda times the L2 norm of the w. W, and for the L1 norm, it's just the L1 norm of the w. So it might give you, a little bit better understanding of this, of all the objective function, but still not good enough because it's just so big idea. So I have an example on the next slide. So let's see it. Okay, so for this picture, you can see here we want to classify these red circles and the blue circles. So for this classification problem, you can I think you should agree with me because I can find that this black one should be a great hyperplane to separate the red and the blue circles. Okay, so what do you think of the blue one? It seems like it perfectly separate all the points, but it will if you give this model a new data set, it's gonna crash because it's gonna be overfitting. So maybe for this black curve, the hyperplane should be a quadratic function, which is x squared at most. But for this green one, I guess it should be like more than cubic or even higher order of x. So So with this regularization part, they can easily face this problem. Suppose the green line, the training loss is actually very small, right? Because it fits all the data, so the training loss is almost zero. However, remember this green one contains very high order of x, so the weight, the W of the higher order of x should be very large. So which means for the second part, the regularization part, it's going to be very big. So the first part, okay, it's small, but for at the meantime, so the second part is going to be large. So it's like a trade-off. So it prevents the model to go overfitting. So that's basically my understanding of the overfitting part. So and people usually treat the underfitting as high bias, which means you are following from your type, and this overfitting and the high variance, which means it works okay on the training data set, but if you have a test data set, it's going to crash. So when I get into this machine learning field, I didn't quite get this. Everyone is talking about bias variance trade-off, and I didn't quite get the meaning of it. And I checked the textbook. All of them are fancy formulas, fancy mathematics, and it's very hard to follow. So until I found this picture from one guy's blog post.
So I don't want to comment on the previous slide that you had.
What?
So just want to look at comment on the previous slide. So basically your green line is got a lot of this discontinuities or it's not smooth. Right?
Yes.
So the regularization is really imposing smoothness straight on that curve. So you're saying rather than having something very jagged, you want to keep it smooth.
Yeah,
so that's another way of looking at it.
Yeah, good. So now see this figure. I think the upper left picture. It's it's a perfect. So and then we are going to reach it in real life because it's very hard. It's just the perfect condition. Also, we don't usually we won't fall into this one because we have so many logarithms, so we can do much better than that. So usually our logarithm or our model will fall into this part. So either it's low bias or low bias and high variance, or it's low variance or high bias. So that's an intuitive understanding of this bias and variance trade-off. Okay, so by now we finished the supervised learning. It's a quick review. So let's talk about the regression tree, which is the second part I mentioned. I will do some quick review. So I have a real life example. So suppose this is me, my girlfriend, my grandpa, my mom, and my father, and the input is the age of everyone, the gender, the occupation, and some other features of us. So what we are trying to do is we want to decide whether the person like to watch the Game of Thrones. So for this kind of problem, we want to use a what's it called, regression or a classification tree. So suppose we have a tree like this. First, the first split we split from whether the person is over 26 or not. So it split me, my girlfriend, with my parents and my grandpa. And for the second split, it's female or not. If it's me and my girlfriend split, you can find that there's a score here. Usually this one is called prediction score. Usually for if the output is continuous reliable, usually this one is the mean of all the samples in this if. and also for a classification problem, this one should be the generic index of this group. So for different problem, this definition of the score is different. So I just put some random score here. The more positive means the more likely this guy's gonna like Game of Thrones, which should make sense because me and my girlfriend should like it, and my parents or grandparents maybe haven't heard. So this is one tree, one regression tree. We have different splits. Okay, so what if one tree is good, but what if we got another tree? So this is the previous tree we got, and we got another one. So for the second tree, there's just only one split. It says which TV did it. So me and my father, we don't usually watch TV every day, but my mother, my girlfriend, and my grandpa, they watch TV. So for this split, we got two groups, and also we get the predicted score of each group. So what we did, so we got two trees. So how we're gonna ensemble it? So usually for the ensemble of tree, it's just we took the sum of the score of different trees. So for me, as an example, in the first tree, my score is +2, and in the second tree, my score is 1.5. So my final score becomes 3.5. And for my girlfriend, her in the first tree is 0.5, in the second is 0.2, so the final score is 0.7. And you can get again from that. Okay, so this is
Sorry, can you say again how you remember that?
Oh, it just you got two trees, so you want to ensemble all of them. So what you usually do is to sum the for me in the first tree I got a score of +2. In the second tree I got a score of 0.1. So you just sum it together prediction score. So it's just the principle of ensemble different trees. So okay, so basically what we have reviewed is the problem of supervised learning and also the regression tree, or also called classification tree. So now let's do some technical part, which is so mathematics here, but this is called the boosting algorithm for regression tree, which is the gradient boosting machine. I think you remember XgBoost is the variant of gradient boosting. So first we learn something from gradient boosting, then we see how the difference they are. Okay, so the boosting algorithm is starts from, we make the first prediction, we set the first prediction to 0, and also we set this R, we call it residual to the Y at the first. So basically, for B, if suppose we want to build B tree, number of B tree in total, and for each round, what we do is to fit a tree to the training data set of X and R. Suppose for the first round, the data set should be X, and this R should be Y. So for the first round, it's just our training data set. So because at first we set the initial value of R equal to Y. So which means the data set, training data set is X and Y. So just our training, basically just our training data set. And what we do is after we fit a tree, we update the output or prediction by adding a shrunk version of the new tree. So it's like f hat of x becomes f hat of x plus lambda times the tree. So it sounds more like for the first round, at first fx of x is equal to 0. So basically in the first round, this f hat of x becomes lambda times f(b) of x. So after that, we update our residual. So suppose that first I equal to 1. So right now, we update this residual to this I minus lambda times the the prediction of of our of the tree we just trained. So after that, after we update it, we go to this step. See that we can build another tree into this training data set, which is x is also the same, but this r is gonna change because we have already changed it here. So did you get feeling of this boosting stuff? Because for random forest or other regression tree, what they did is they only fit a tree to the training data, and every time it just fit the training data. So that's at the very beginning I said, instead of trying to fit the data into the large data set into the whole tree. This one is just learn from each round. This is mathematical, so a little bit hard to explain. How do I control shrinkage? Okay, you mean the lambda, right? Yeah, actually, this is a preprocessing of what you usually do during the machine learning process. Actually, you can. I'll show you in the code. Usually, you just do the calls, and for each tree, you use different parameters to see the final score, which one is better. So, but it has this shrinkage parameter usually has some default value, which is for each package we also have some default values. So usually the default value is about 0.01, I think, for the gradient boosting machine. So yeah, I think that's it. So this one is for the gradient boosting machine. So let's see the boosting algorithm for XgBoost. Also, we have plan to have total number of B trains. So we also start from consistent prediction, which is f hat of 0 equal to f hat of x of the first round is equal to 0. But instead of adding a shrinking version of the new tree, this time we just add a new function. So the process is actually quite similar. So maybe for a second tree, it's 0 plus a new function, which is because 0 actually is the first tree, right? So you can substitute 0 to the first tree here and plus f1 fx. So for the second tree, it is like the f1 x plus f2x, which is you can substitute f1x, substitute f1x substitute f1x to here because the prediction tree, because this one is 0, so f1 hat of x is actually equal to f1 of x, so you can substitute it here. So the process looks quite similar, but as I mentioned, the only difference of this XgBoost, the only difference between XgBoost and the gradient machine is that for each round, it's just add a different function. So for this one, for XgBoost, it just add a new function. So what XgBoost is to find this function. What is the best function to add, and not like the gradient boosting. It's fine. It first fit a tree to the data set, then they shrink the version of it to the output. So you can see it's just a sum of all the shrinking version of the fit tree. So you can see the final result shows similar. It's just a sum of all the shrinking version of the trees, and for the XgBoost one, it's also the sum of something, but just the different kind of thing. So at least this is my understanding of what is XgBoost different from traditional gradient boost machine, and those guys can find this is where you need to decide each function, which is the function you need to find. So actually, there are lots of mathematics, in this how to divide this perfect function to find. But I think most of us should be more interested in how to use this XgBoost to do this kind of computation. So I think that's all for the to explain the principle of XgBoost. So right now I want to show the code I use to do the computation. Did you close my? So how many of you have used this Python or Go before? Yeah. Okay. So the first column, first of all, we just import some data like require in SDD. Okay. So the second part is reading the data. So it's a trim.csv and another one called test.csv. So let's first take a look at this trim.head. So let's see what's coming in training data set. So the first column is called ID, which is the ID of the insurance case, and the second column is the hazard score, which is the Liberty Mutual Group. They define this hazard score to tell the agent whether this case has some problem or not. If the hazard score is very high, which means this case might have some problems, so you need to take a closer look. So this is what is the output of our model, and they want us to model it. So for the other columns, you can see all of them are anonymous. We don't know the name of these columns, so you can see it's from T1V1 to this T215. So could you get any guess of what this column?
I'm waiting more time with it.
Okay, yeah. Just because they made it anomalous to don't let that's a secret. So it's fine. Let's check the size of this data set. So for the training data set, it has 50,000 rows and 34 columns, and you can see for the test data set, it's actually quite the same, but just without the hazard score, which is they want us to predict. So all the other predictors they are the same, but just without the hazard score. So let's do some data cleaning part. So here, what I did is first I get rid of this. I get the output out of this training data set. So this is labeled to train.data set, train.header, which means I took the header column out of this data set, and also I get the test ID out of this test data set. Finally, I drop this ID header from this the training data set, and drop the ID from the test data set. So right now I'm using the pandas. I think in our deploy it's the same option. So let's do that. Okay. So let's see what happens if I after this preprocessing on training data. You can see for the training data set we don't have this ID, and also we get rid of this header score. What left is only these training these predictors, and we can see the similar thing for the test data set. Okay, so most of them are clean. So no ID, no header score. But yes, but there's a problem here, because you can find that some of them are numerical, some of them are categorical data. So what if you have encounter such a condition? What you should do for this kind of stuff? You have both numerical data and categorical ones.
Are you choosing into dummies?
Into dummies, that's a good one. So in Python, what we did is this train.t2 dictionary is it's a function of pandas. So what it does is to transfer this huge data set into dictionaries, and after that we transfer the list of dictionaries into sparse matrix, which is just as you said, it's doing double variables. So I think that one doesn't make any sense. So I have a very small example here. So you can see here, this is my example. It's a list of dictionaries. So suppose you can see for the first dictionary, the city is Dubai, the country is 33. For the second dictionary, city is London, country is 12. For the third one, city is San Francisco, country is 18. So for our data set, if we use this to-dict function, actually it will return a list of dictionaries that suppose for the first row, for the first dictionary, it will say T1U1 equal to 2, which is like here, city equals to Dubai, kind of small simulation. So you can see what if I do this phase transform, it's just very similar like this. It's the same function but I use it to a different data set. So let's see what I got. Oh, sorry, I didn't do the previous one. So it's going to take about 10 seconds. As you can see here, it's running. So okay, so let's see the result of this. Okay. You can see it transferred this list of dictionaries to a numpy array, and you can see for the fourth dictionary it becomes 1003. So which basically says there are 3 levels of this city. So it translated to split this feature into 3 dimensions. So if the name is divide, it's becoming the first one is 0. If the name is longer, okay, the second one is 0, and the San Francisco, okay, the third one is 0. So, and also we can check the the feature names, of it, which is kind of city to divide. So city to divide, okay, it's one with city to divide. So this is just 3 categorical ones. Suppose we have a more than 20 or even more number of categorical data. So which means this matrix is going to be very sparse, right? So actually, this XgBoost it mentions that it loves sparse matrix because for sparse matrix you can use the single value decomposition to boost the calculation. So actually it's good. So okay, so right now we have done the pre-processing part. We transfer all the categorical data into a sparse matrix. So we are ready to shift it into our XgBoost module. So here I will build just build one XgBoost model as an example. So here first I define a dictionary called parameters. So there are lots of parameters for the XgBoost, so I'm just going to mention just a couple of them. The most important one is here is the objective parameter. It's the object to new regression, and there are other choices you can check on its documentation. And here the one called the minimum child weight is minimum of sum of instance weight needed in a child. So when you split the tree, sometimes that you don't want to go too deep, right? Because there are some conditions you want it to stop splitting. So here is a minimum sum of instances that what I say. If you remember the predicament score, actually it's calculate the sum of the sum of the weight, which is basically the sum of score in a child. So if it's too low, so the process is going to won't split anymore. So and also the maximum depth is to understand it's the depth of the tree, and okay, so then I just transfer this dictionary into a list. And so after that, just a couple other parameters. So for example, this offset parameter is like in XgBoost it has a also called validation or working list, which you can set a validation data set. You can divide your whole data set into 2 parts. One is for training, one is for validation. And XgBoost can take this validation data set to check. It can do simultaneously to check whether this whether this validation error is going to decrease or not. If it's not going to decrease, maybe after 100 or maybe as I said earlier, stopping rounds. If the validation error doesn't decrease after maybe 120 rounds, so it's gonna stop working. So let's see. For here, I just transfer this training data set into a D matrix, which is the function that XgBoost used. So it didn't mention much. And you can see I just use the offset to split my whole data set. That I use 5,000 rows for validation, and the other 45,000 for training. So basically that's it. And you can see this evaluation list. Since it's XgTrain, so I define here is Xg value is what I define here. So it's Xg value is used for validation. So finally we can XgBoost train is what we use to train a model, and finally we use this model to do some predictions. And after that, we got the predictions. So the next step is to generate to CSV file to submit to the to Kaggle. And actually this one is going to take a long time. So I just use this output here. So you can see for each round, which means for each tree we are building, it has a training root square and also the validation root square. Okay. So you can see at the I think it's after 100 rounds, it's got the it's meet the early stopping standard, which is the validation root square doesn't decrease in 120 rounds, so it just stops. So I think it's yeah, it's here. Okay, so you can see it's starting at that saturation is around 140. Sorry, so 1,400. So basically is what I have did is build a one XgBoost model, just one of them. So the good thing is you can pick out the model into a binary file. So you don't want to build this model every time. So what you can do is to use this model.save. So to save it as a model. And also, actually I should do that because this one is very long. That's okay, you can see the process. Because my computer is a bit hot and slow right now, so I don't want to do this process. It's going on. So you can see actually it's still running. Okay. So after we train the model, we just save it for future use. And what you can do is you upload the output to the Kaggle, and you can see which position you are on the leaderboard. You just save the name of the file as rank the model. So next time you can just load this model from your local file and then need to train it again. And there's one thing that XgBoost did great is actually you can check the Okay, so it can dump the model into a TXT file, which is I think is very good, and it can show the process very intuitively. As you can see here, for the boost one, which is the first tree we did, and you can see it's for the first split, the feature 81. I think if you remember, there are only about 30 features, so you might want to know where does this feature 81 comes from. So the dummy variable, so it's expand the feature dimension. So you can see for the first split it is the feature 81, and if it is used, okay. So if it is yes, it goes to 1. If it is no, it goes to 2, which is a far behind. So for the second split, you use feature 28, which is if it's yes, it goes to 3. If it's no, it goes to 4, which is far behind. And for the third split, if it's yes, it goes to 7, which is here. If it's no, it goes to 8. So it's kind of you can see the whole process of the XgBoost splitting the tree. So I think this issue is very good to give you an intuitive understanding of how the trees split. Okay. So it's still on it. What I have did is just training one XgBoost model. So in curve computation, usually one model is not enough. Usually people are going to use 10 or even more models to example all of them. So think most of Kaggle did is to build it. You don't want to write all of the code for each model. So usually what you will do is to build a class. Here I call it a train XGB class. And what I did here is for the initial function of this class, I set a couple parameters. The first one is the model index, which is I keep a record of myself. This is the first, or is the second, or the third. And this is Y transform. Is like sometimes the output maybe you can check the distribution of this output. If it's like a long tail distribution, so you probably use a log transform to log transform to the output, so make sure it's be a normal distribution. So this Y transform parameter here is used to if you want to do some transform to your output, so you just put it here. And the next one is the feature transform, so which is the most important part of this I'll say of this building of this computing in this Kaggle one. Actually, this one is the difference between top 10% players like me with those top 10 players. So actually, most of them are spending more than 70% of their time doing this feature engineering stuff. So for here, we can do some transform feature one, which is just a kind of function right here. So for different features, maybe for this example, maybe you want to try. Okay, what if I remove all the categorical data out? What if I transfer the categorical data like it does it as factor, blah blah blah. So it transfer the categorical data into one to the number of levels it has. So there's something like this part you're in some experience, because for different data you gotta to have a sense of how to transfer the feature is gonna be the best. So it's really some experience, but I just write some template functions here to. What I did is actually don't matter, but this is what people usually do is to define a couple of feature transformation functions here, and so you can see here if the feature transform equal to 1, we just do we transform this train and test set according to the function, and then we transform it onto this function. So this is basically the processing one, and next is the fit function. Actually, you can see if the Y transform equal to log, so what you do is to transform the output, doing the log transformation to the output, and that's actually the other part is not that hard. You can see it's Peter is the stuff about parameters. Is what I pass in doing the initialization. I pass all the remember the parameters of XgBoost into the class. So they use this this kind of parameters for XgBoost, and then does the training part and then assign it to Okay, so after training, you just did some prediction part and for the Y, and so you need to transform back to your output according to what you did in the preprocessing part. Okay, so yeah, that's after you do the prediction, you write it to the file and send it to the name you want. Okay, finally you define you define build function, which is basically the preprocessing, the fit, and the predict, which is the whole process. And you can see if you have a class like that, you can just set a parameters like this one, and create an object of XgB, and pass all the things you want into this class, which is doing the initialization part, and just call the build function to build the model. And so this code is very short because you can write this similar code 10 times or maybe even more to do to generate all the models. So actually what I did is I generate about 10 or 20, and I pick only generate 20 of them, just pick about the best 10, and I do an ensemble method to assemble them together. Actually, I don't assemble any random forest or gradient distribution model here, because in this competition the XgBoost performs so well. So XgBoost model itself actually is pretty good. So I don't assemble other machine learning. So that's basically what I have in the competition. So I hope we can discuss a little bit. So what you did in the competition or your understanding of XgBoost.
Okay, make your time. I want you guys to try it. Do you have as a notebook and stuff? It's fun. Try to.
If you copy the code to the text editor, and then just it's almost always just ask us just for show you the code.
Any question? Which part is the most difficult part?
Okay. Actually, building the XgBoost model is not difficult. As you can see, the code is quite short. But what I want to say is the feature engineering part, which is what I think, the other part actually needs some more experience, because some of course followers, masters of Kaggle, what they said is, we're going to do more tests and try what you can, and basically those trials is based on your experience. You get a sense of the data, maybe you have experience in handling it, so you know which transform is going to work. So actually my I think that's a feature. Actually, that's interesting. I don't think so in this company, because all the variables are anonymous. You can see, So if it has a name, you can intuitively. The first step of feature engineering is to do it intuitively. That's
how about just using other criteria to read out the features?
Yes, actually.
Information or things like that, right? So what
kind of.
Minimum relevance, maximum relevance.
In random forest. Exactly. Because actually in R you can do that, because in R for random forest it transfer suppose for the category data. Actually after you do the two vector function, actually the feature actually it's the same, not like Python will transfer to dominant variable. So suppose you have one category data, and you transfer to different features. So that's why the matrix gets bigger. But for R, you can do that. I'm not sure why it's different in scikit-learn and R, but in scikit-learn I cannot reproduce that result. So by R you can get the importance of the features from top to bottom. So you probably want to remove the least important ones. That's actually what I did.
Yes, so how sensitive is the XgBoost technique to modeling features? Like you just have some, if I just put a column or diagram, okay, diagram noise, how will it affect your class on
I think what the tree model is good at is what XgBoost is good at. So for the linear regression and the tree model, for tree model you don't get a formula or a equation after training. So, but it can show the processing tree data to the power of the tree model. So I guess. Oh, okay. So you mean for the model data, right? I think this.
Well, this is relevant. So maybe some column in the data is not relevant to your classification at all. So then there's your technique depend on that, and so that could be an issue, right? So you might have to just figure out that I don't want to use this at all.
Yeah.
That might improve your accuracy.
Yeah. That makes sense. Yeah, I would need to do
Yeah,
it.
you're right about there's no semantics to the data you don't have yet.
Yeah.
Mask all that out.
Yeah.
And apart from that, you use techniques like this.
Yes.
This is one type of feature.
Yeah, that's right. Good answer.
But a lot of people don't know this is not work. You try and see the
Yeah. So that's a lot of people say the key to winning Kaggle competition is that you know how to do it, then it's just either you get a very good machine or you use the animal web service, then you got lots of time. Okay, that's it. So that's why people don't like Kaggle competition anymore, because a lot of Kaggers talk about it on the forums and say this Kaggle competition is becoming losing its credentials or credits. Yeah, they're different.
Oh, okay. But what about the actual execution time for this data set that?
Actually, it's not. It depends on how many models you're going to train. For just one model, it's about, I think it's like 2 minutes. The data set is not that big. It's just megabytes, not even gigabytes.
Yeah, so, this data set is that.
Yes, but it's just for this competition. For other one, it doesn't count.
Is there are there a set of algorithms that kind of look over the search space of feature design that kind of test these 200 features and run them all 200 times? Is there some method for doing that?
You mean apart from XgBoost?
Yeah, like you said, the important part of XgBoost was doing the feature design.
What do you mean by design?
Feature engineering.
Oh, feature engineering. Actually, I'm not a perfect in that field in feature.
That's like combinatorial problem, actually, in the power set.
Yeah, I should do that. I don't know why I like
possibilities can be used.
But if you're looking at a Kaggle computation and you have scrubbed and anonymized data, how else are you going to do it? Randomly,
I don't know what feature it is. How many columns are there in data? That we remember offhand, how many columns of the data?
Scroll up. I think it's here 55.
Okay. And the columns is 33 columns.
There's something in convolutional neural networks called swarming, where swarming, if you look at Unity.com and you get a swarming algorithm, it's doing feature design and that's I don't really know anything about the algorithm.
Okay, because running out of power, I don't know. Just
Any more questions, guys? We can start with XgBoost to
They're already using it actually. Actually, in our I think last month the XgBoost got banned from CRM because they have some problem running on Windows. But right now it's better. Yeah, but right now it's better. I can just install package XgBoost.
And previously we have a session about how to use XgBoost R package. And by the author who wrote the XgBoost package by our employee. So you can check out videos too.
Okay, where is that? I was trying to look for that.
Go to our channel, NYC Science Academy channel, and find that.
What can we find each other?
NYC Science Academy.
Or
No, it has more than 2,000 videos.
oh, you didn't start. Because I was looking at I talked to that presentation in July, and I couldn't find it at that time. You said you were performing.
Yeah, yes.
It was put up. Okay, I can do that. You ask me about that. Okay, thanks. I'll be happy to see that. Okay, that's good.
Guys, thank you for coming.
Yeah, thank you. Very good.
There's free tacos on the 19th floor.
Everyone,
10 beers.
I actually feel that.
All
right, that's great.
It's rework.
Yeah.
That's why they're doing so well.
Thank you so much.
Thank you very much.